In the next part of lesson 7, we're going to look at another linear program. In this one, Juan makes two types of wooden clocks to sell at a local store. It takes him 2 hours to assemble a pine clock. X is the number of pine clocks he assembles, which requires 1 ounce of varnish. It takes 2 hours to assemble an oak clock, which takes 2 ounces of varnish. Y here is the number of oak clocks. Juan has 14 ounces of varnish in stock and can work 20 hours. If he makes $3 profit on each pine clock and $7 on each oak clock, how many of each type should he make to maximize his profits? Well, the time constraint, he can work 20 hours. The varnish constraint, 14 ounces. If he spends 1 hour on making a pine clock, they'll take him 2 hours. If he makes 2 pine clocks, that'll take him 4 hours. If he makes 10 pine clocks, that'll be 20 hours. So in terms of his time constraint, we're going to first multiply 2 times x. And then we look at the oak clock. If he makes 1 oak clock, that'll take him 2 hours. If he makes 2 oak clocks, that'll take him 4 hours. If he makes 10, that'll take him 20 hours. If he makes Y oak clocks, that'll be 2 times Y. So we're going to add 2x plus 2 times Y. He can work up to and including 20 hours a week on pine clocks and oak clocks. Now for varnish, for the pine clock, it requires 1 ounce of varnish. So if he makes 1 pine clock, he uses 1 ounce of varnish. If he makes 10 pine clocks, 10 times 1 is 10 ounces of varnish. If he makes X pine clocks, X times 1 ounces of varnish will be needed. So we're going to write this as 1 times X. For the oak clock, he needs 2 ounces of varnish for each oak clock. So if he makes 1 oak clock, that's 2 ounces of varnish. 2 oak clocks, that's 4 ounces of varnish. 3 oak clocks, that's 6 ounces of varnish. Y oak clocks, that's Y times 2 ounces of varnish. So 2 times Y. And then again, he has at most 14 ounces of varnish. So he can use up to and including 14 ounces. Now to get the intercepts, I'm going to come over here to Desmos and I'm going to type 2x plus 2y less than or equal to 20. To get the less than or equal symbol, you type the less than symbol right next to the M key, and then press the equal key, and that turns less than symbol next to the equal symbol into less than or equal to in Desmos. Notice when it's just less than, you have a dashed line here. That means you're not including the line itself. When you type equals, you're including the line itself. Now I got to solve that for x to get the x-intercept. The x-intercept is where y is 0. So what I'll do down here is I'll copy this and I'll replace this with equals. I need to get the x-intercept. So what I'm going to do here is I'm going to multiply this times 0. Right? So I need y equals 0 to find out what x is when y equals 0. So 2 times 0 is 0, and 0 plus 2x is 2x. Now we just divide both sides by 2. If I divide the left side by 2, I can divide the right side by 2. And then 2 divided by 2 is 1, and 1 times x, well, that's just x. And so when y is 0, x is equal to 10. We're going to write this as 10, x is equal to 10, y is equal to 0. And then we're going to close the parentheses. All right, now we're going to do the same thing for the varnish constraint. It equals, we're going to do less than or equal to 14. I'm going to copy this whole thing. I'm going to change that to equals. Now, x times 1, that's just x. I want to find the x-intercept. So I need to replace y with 0. We want to know what x is when y is 0. And then 2 times 0 is 0. X plus 0 is x. X equals 14. So here we're going to type parenthesis 14 comma 0 close parenthesis. Now we need to get the y-intercepts. So for the y-intercept of the time constraint, I'm going to copy it, change that to equals. Now I want to make x 0 so I can find what y equals. 2 times 0 is 0, and 0 plus 2y is 2y. Now I divide both sides by 2. And then 2 divided by 2 is 1. 1 times y is y. So y is 10, right? When x is 0. So when x is 0, y is 10. Okay, now we need to get the y-intercept of the varnish constraint. We want to know what y is when x is 0. So we're going to replace this with 0. 0 times 1 is 0. 0 plus 2y is 2y. Divide both sides by 2. 2 divided by 2, well, that's 1. 1 times y is y. And so when x is 0, y is 7. This was generated in Desmos. This is the time constraint. The x-intercept is what? When x is 10, y is 0. What's the y-intercept? When x is 0, y is 10. Okay, for the varnish constraint, the x-intercept is 14 comma 0. So when y is 0, x is 14. And then when x is 0, y is 7. Now to make this graph look like that graph, I need to make the blue line purple. And I need to make the red line, well, red. Also, I need to add the non-negativity constraints. X greater than or equal 0. Y greater than or equal 0. Now, when I have them listed on different lines, what I'm saying is this can be true, or this can be true, or this can be true, or that can be true. I want the intersection, not the union. In order to do the intersection, I'm going to use squiggly brackets. Then I'm going to copy each one of these into the squiggly brackets. X greater than or equal 0, squiggly bracket, y greater than or equal 0. And I'm going to change this to equals, to a line. So I'm going to change that to equals. I'm going to change this to equals. Change that to equals. I'll make these black, and this line down here is going to be red, and that one's going to be purple. I'm going to click done. This line 1 says what? 2x plus 2y is less than or equal to 20, and 1 times x plus 2y is less than or equal to 14. I can actually write this as x plus 2y less than or equal to 14. And x greater than or equal to 0, and y greater than or equal to 0. Now, the reason why I have these down here is because I want the lines drawn so I can get the vertices. And it allows me to click on points of intersection. So the vertices of the feasible region are these 4 dots. And that looks just like the one in my open math. So the vertices of the feasible region, I'm going to click them right here. They include two intercepts, the intersection of the lines that correspond to these two inequalities, and the origin. So I'm going to type them right here. So first you got 0, 0, 0, 7, parentheses, comma, 6, 4, close parentheses, and then 10, 0. Now, when you hit enter here, it messes up our graph. But I'm going to refer to this graph over here in Desmos. Now we want to find the profit function. If he makes one pine clock, that's $3 in profit. If he makes 2 pine clocks, that's $6 in profit. If he makes 10 pine clocks, that's $30 in profit. If he makes X pine clocks, that's 3 times X dollars of profit. So the first part is 3 times X. I'm going to write that as 3X. How much profit does he make on the pine clock? Well, if he makes 1 pine clock, 1 times 7 is $7 on that one oak clock. If he makes 2 oak clocks, 2 times 7 is $14 on the 2 oak clocks. If he makes 10 oak clocks, that's $70 in profit. If he makes Y oak clocks, that's 7 times Y dollars in profit. So we're going to add 3X and 7Y. Okay, so over here in Desmos, I'm going to type, I don't know, some profit level. Maybe we'll start out at 0, equal to 3X plus 7Y. I'm going to change this profit function to green for money. Now, as I raise this profit up, what happens? As I keep raising the profit up, that green line gets pushed out at 60. You can see this green line is flatter than this purple line. The green line slope is smaller than the red line and smaller than the purple line. So the optimal solution here is going to be this point, 0, 7. So if I back this down to say 49, it looks like 49 works, right? If I zoom in on this point, you can see that the green line is just touching this purple line at this intercept, 0, 7. Now we can verify that this is the optimal solution by doing what? At this point here, X is 0 and Y is 7. So I'm going to type 3 times 0 plus 7 times 7. Y is 7 when X is 0 at that point. And we get a profit of $49. So we just verify that this is, in fact, our optimal solution. So this person should build 0 pine clocks and make 7 oak clocks, which produces a maximum profit of $49. Now, let me just show you something here. Let me reset the profit to 0. Suppose demand builds for pine clocks. Maybe we go into recession. And that goes up to, say, $4. Maybe this drops down to $6, right? Now what's going to happen? As I add dollars to the profit side, the line pushes out, doesn't it? Now we're beyond the feasible region. So let's back it up a little bit. Let's go 48. Looks like 48 works, right? Notice that the slope of the green line is now between the slope of the purple line and the red line. And the point of intersection is 6, 4. This profit function, the green line, intersects the two constraints at this point, 6, 4. So let's just verify the profit is in fact 48. I'm going to copy the right side of my profit function here. And then I'm going to plug in the values for X and Y at this point. We're making 6 pine clocks, so X equals 6, and 4 oak clocks, so Y equals 4. So we're going to replace that with 4. I'm going to replace this with 6. We just verified the profit is 48. Now, what happens if we go deeper into recession? Well, maybe the oak clocks drops to 2 and the pine clock profit drops to 3. We're going to reset the profit at 0. I'm going to change this to 0 and this to 0. I'm going to change this price to, or this unit profit to 2 and that unit profit to 3. So at 0, 0, we have 0 profit. Now, as I increase the dollar side of the profit equation to 10, to 20, to 30, notice what happens. Now the optimal solution is where X is 10 and Y is 0. The profit function is really, really steep. Its slope is much larger than both constraints slopes. So 10, 0 ends up being the optimal solution. And we can verify that by plugging 10 into here and 0 into here, and we get 30. So the way linear programming works is it doesn't use the slope of the non-negativity constraints. We ignore the slope of these two constraints. The other constraints, we calculate their slope. We calculate the slope of this, we calculate the slope of that, we calculate the slope of the profit function, and we compare the slopes. If the slope of the profit function exceeds the slope of the two non-negativity constraints, then the optimal solution is this corner point. If the slope of the profit function is in between these two constraint slope, then this is the optimal solution. If the slope of the profit function is less than these two constraints slope, then that corner solution is the optimal point.